Welcome back to this chapter. We will focus in this part on a section that is really very important synthetically and mechanistically. It's 13.10, ring opening reactions of epoxides. So epoxides are very useful intermediates. We had noticed that this is a three-membered ring with oxygen being part of the ring. Now, because this is a strained ring, that makes it also very reactive towards both weak and strong nucleophiles. Here are a couple of examples of strong nucleophiles that you should remember from Orgo 1 in previous discussions. Grenary agents are those reagents that have a magnesium and then an X, so that can be chlorine or bromine. And this is basically a source for an R minus, which is a strong nucleophile. Hydride reagents, we can utilize things like sodium borohydride and lithium aluminum hydride. All of these are sources of hydride, not to be confused with proton. This is a hydride. This is actually nucleophilic. Alcohols, they are not as strong, but remember that in the alcohol functionality, we do have nucleophilic characteristics through one of the lone pairs on oxygen. Alkoxides are stronger than alcohols, so alkoxides are basically RO. And I'm going to use lines here. You're permitted to use lines. So of course this is a much stronger nucleophile than the corresponding alcohol. And we can utilize this in epoxide reactions. Please notice that this nucleophile can be wrapped up and the reagent might say something like ROLI. Let's say it's CH3ONA. You need to know and pull out the corresponding nucleophilic component for the mechanism. Here we have an outline of strong nucleophiles, hydroxide. So if you were to try to use NaOH as reagent, sodium hydroxide, we are attacking either side, in this case the equivalent. There is an important discussion as to when this is not a simple oxyrane or epoxide, which side is preferred, but that's not the case for this simple ethylene oxide. So we now have a nucleophile that opens up the ring strain. Ring strain is gone, makes it more stable. We then have basically, we have reallocated. It's always good to draw Lewis structures, which means you show all the lone pairs. Now you see that, oh, we end up with 3 lone pairs. So we're not magicians, we don't make them appear or disappear. It's good to keep track of them everywhere, okay? So once we have opened up the epoxide, we get the O-. The O- is then part of the protonation process. So again, two-step procedure, nucleophilic attack, then proton transfer. And here again, we also talk about this being thermodynamically favored due to the relief of ring strain. Here's a diagram that outlines what happens. So here, epoxide, high in energy, meaning more reactive. Once we react it, we get an alkoxide. This is low in energy, more stable. Okay, so that's why we say this is thermodynamically favored. The high reactivity of epoxides also make them as important, it means epoxides serve as an important synthetic tool, especially when we're trying to elongate a chain or add a net 2 carbons. More about this later. Now this is a busy slide. You may want to pause here and think about which one is the nucleophilic species. So pause, write down what that nucleophile is, work through the mechanism, and compare with the products. So as I said before, so this would be RO-. I'm going to use lines again because it's faster. We can use CN-. We can use SH-. Here we have R-, and here's H-. Okay. On this slide, actually I should say here there was a line, ring opening of epoxide is regioselective and stereoselective. We don't see it with this simple ethylene oxide, but when we have different substrates, different epoxides or oxiranes, we need to pay attention to detail. What is that? So regioselectivity means that when we open up the ring, remember how the mechanism is actually akin to an SN2 reaction, which is studied in Orgo 1. And we want to actually then attack the least unit carbon because of sterics. Let's just take this 1,1 dialkylated epoxide. 2 methyl groups are bulkier than 2 hydrogens that are not drawn here. And we now see that this is less hindered, and the nucleophile will actually now prefer, and I prefer you always draw, your electron pair. So that now you can draw the mechanism. So this opens up. The second step is protonation, and here we go. Now, stereoselectivity has to do with SN2 requiring inversion of the configuration, meaning the stereochemistry. An up becomes down, or an up is approached from a down phase, and a down is approached from a top phase. So when we have our nucleophile attacking, again, let's fill in those important electrons. That's what makes this nucleophilic. This will now prefer to attack from the opposite side of the epoxide. Okay, and now we see that the nucleophile is in a trans relationship to what ends up being the alcohol. So this stereochemistry here was basically inverted through this process. Remember that skill builder review practice is very important. Practice, practice, practice. It will be very helpful. So here we see it. Here we see another mechanism. Now we can have, instead of strong nucleophiles, we can have acidic conditions. So what does that mean, acidic conditions? Especially with weak nucleophiles, we basically need to activate. So proton transfer, protonation, means activating the oxygen, therefore weakening one of the bonds and making it easier for a less nucleophilic species to now open us up in an SN2 fashion, as we have seen before. So we can have weak nucleophiles. Water and alcohol actually lead to this reaction when we add trace amounts of acids to catalyze the reaction. And then here we see an outline. If we take water as the nucleophile, so you see this in red, it's a net transfer of OH. If we have an alcohol, it's a net transfer of OR. The attack is opposite. In this case, it doesn't matter because it's a simple oxirane or epoxide. And so we have protonation, attack by water, and then deprotonation leading to the product. So in this case, we see we're forming a diol, and here we're forming an alkoxy alcohol, right? So this is a 1-2 relationship. Antifreeze, which is ethylene glycol, can actually be made industrially by treating this with sulfuric acid. Square bracket means it's a trace amount, it's a source of H+ as a catalyst to form ethylene glycol. Here we see the mechanism that I had just outlined, now written out in detail. Nucleophilic attack on a hydronium ion. You may also draw mechanisms like this. So this is basically the same transformation. So it's a net proton transfer. We then have the nucleophilic oxygen and alcohol in water attacking one of the 2 carbons, quenching the charge at the other end. The 3-membered ring opens up, and then the last step is to take back that proton. So proton transfer, SN2, proton transfer. Now, we need to look closely at the substrate itself. Under acidic conditions, actually, the preference now changes in terms of attack. The nucleophilic attack still occurs at the less substituted carbon if we have a primary and a secondary carbon present. So that would be a primary position here, this is a secondary position here. We have protonation here and a net attack then on the protonated cation by X-, and it leads to the structure here. However, if we are now dealing with a tertiary carbon, so this would be with having two substituents on one end, now the nucleophile attacks in a different fashion. What's happening here is that basically this bond is weakened after protonation because there's a partial higher substituted carbocation characteristic forming. So the nucleophile in the end attacks here, and you get this overall transformation. So here's what I had just said in a little bit more detail. When we protonate, we actually now have a kind of an unsymmetrical situation. There is more positive character on this carbon, which is tertiary. So a tertiary carbocation is more stable than a primary. So it kind of pulls this back and forth, therefore making it easier for, let's say, X- to attack in that position and open up that bond. So that then explains this. So if a tertiary carbon is not present, the sterics will dominate. But remember that when we're looking at these two situations, primary, secondary, primary, tertiary, we either have the steric effect dominating and attack on the least substituted site. It's less crowded. If we have a tertiary carbocation, then there is an electronic effect because a partial positive charge on this carbon is more stable, making it more conducive to attack by the nucleophile. And then here we also want to make sure to remember that we're dealing with inversion of configuration in ring systems and other substrates. So remember, depending on the substitution pattern here, the example is first protonation, proton transfer, weakening this bond here, making it more susceptible to now by an attack of ROH, as outlined before. And so you can practice drawing these mechanisms. I've added a slide to this topic because there are some very important applications or consequences in real life. There are compounds known as benzoate pyrenes or pyrenes. They are polycyclic aromatic compounds. I had mentioned before, we've seen this before, that epoxides are key intermediates. They're highly reactive and we can make many substituents, but they're less stable and therefore more reactive. Now, what happens that sometimes we can actually consume something and it turns out this is a component in tobacco. Tobacco is really bad for the lungs because it basically can lead to cancer and change the genetic material for offsprings. Now, why does this happen? Sometimes what we ingest is not toxic, but because how the body then metabolizes it, it makes it more dangerous. So what this means is that in the liver, we have liver enzymes like P450, and they're known to oxidize substrates, make them water soluble to eventually excrete them. Now, in this case, it means that there are two double bonds that can be transferred into an epoxide. So you see one epoxide here, and you can see that this can be derived from an epoxide that then opens up. And turns out that this here is really very nasty. Why? Well, let's just think about what we are full of. Our bodies are full of nucleophiles. So if we say that we have here our DNA that is a nucleophile, it can now make a covalent modification, therefore changing the helicity and their broken pieces within the DNA and RNA material. I'll meet you in the next portion.